Okay, so in the last class we had seen that the Hamilton's approach provides a nice way of writing the first order differential equations, and in that method, the Hamiltonian method, we write first express T and V in terms of what? P and Q. In the Lagrangian method, we wrote it in terms of Q and Q dot. So, there lies one difference. Then you obtain the partial derivatives. Oh, H is just T plus V, then write the Hamiltonian function H as T plus V. Then you obtain delta Q and right. Once you have done so, or because there will be different directions, do not talk, there will be different directions, and so you will have to take the derivative of the Hamiltonian function with respect to each of these, and then finally once you have done that, the equations would nicely be expressed as Q I dot is equal to and P I dot is equal to minus okay. So, this is the essential technique. Now, you have seen that in some cases these equations will yield dotted terms in the right hand side, which again you have to substitute from here in order to express in terms of undotted terms. So, that is the essential technique. But now, so far we have solved problems that are more of the circuit or sort of physics oriented, and that might erroneously give you an idea that this method is, these methods that I have discussed so far, Lagrangian and the Hamiltonian, these are not all that much useful in engineering systems. So, today let us attack an engineering system right away. Most of you are electrical engineers, so let us do a electrical engineering problem, a DC machine driving a load. So, what is the structure of the DC machine? You have the armature. Okay. The armature is fed by means of a supply, a DC supply. There will of course be some resistance and inductance of the armature winding. So, let us take that out, so that we can directly see that they are in the circuit. So, that is the armature circuit. Assume that the field is constant. We will later assume that the field is also variable, but to begin with, let us assume that the field is constant, which means it could be a permanent magnet machine or a separately excited machine. And you have applied a voltage, say E, to this, and this is what the inductance of the armature, resistance of the armature. Now, here this fellow rotates and there has to be a mechanical system to it. So, from here there is a shaft, and the shaft is moving something, say a disc with some mass against this. Okay. Now, this armature has a mass or moment of inertia, assume that to be I1. Here there will be a bearing, and bearing will have some friction. So, assume that to be R1. Similarly, here this disc will have a mass or moment of inertia, call it I2, and these will have another bearing friction called R2. Fine. There is another degree of freedom. You might notice that these two are not moving exactly in step. There has to be some kind of a springiness of the shaft. So, that is represented by a spring constant K. If it is not there, if it is rigid, then they will not have their own independent degrees of freedom. So, in order for these two to have their independent degrees of freedom, this fellow should be slightly torsionable. So, there will be a torsional spring here. So, suppose this is the system. How do we represent it in terms of a set of differential equations? Fine. First, let us identify what are the variables. This is the electromechanical system. The main advantage of whatever we are doing is that you know the methods of writing the differential equations for electrical systems, you know it for the mechanical systems individually, but when you attack a electromechanical system, then these methods are very handy because they treat them in the same way. Good. So, what are the state variables? What are the variables in the system? We are trying to identify the minimum set of coordinates. Tell me what are they? Here there will be a current flowing. In our notation, we will consider the charge flowing here. The electrical system will it need any other variable? No, one will suffice. How about the mechanical system? We will need the position of this armature and the position of this, that uniquely identifies. So, there will be a position coordinate q, say let us call it q1, q2 and q3. So, these are the position coordinates. Position means angle essentially, and q2 dot will be the angular velocity, q3 dot will be its angular velocity. Fine. Now, notice that the electrical system and the mechanical system, how are they coupled? I am not talking about the physical coupling, I am talking about the mathematical coupling between them. How are they coupled? The electrical system applies a torque on the mechanical system, and the mechanical system responds by applying a back EMF on the electrical system. That is how they are coupled. Fine. And what are their these couplings? The back EMF EB is K phi, IA is Q1 dot, right, and the torque we will not write it as T because T we are representing the kinetic energy by. So, we will write it as say F is, so this is a torque, sorry no this is my F, is K phi IA is the torque. Back EMF EB is K phi the speed of rotation of this one. So, okay. Now, these two K phi's are in fact the same, these two K's are in fact the same. That is what if you assume that the power input into the motor is equal to the power output out of the motor. If you ignore the losses, then these two are actually equal, else there will be slight difference which you can ignore for now. So, these two are the relationship of the interaction between the mechanical subsystem and the electrical subsystem. Now, one convenient way of handling this would be to assume to handle the electrical subsystem and the mechanical subsystem separately. Why? Because then the electrical subsystem will be simply a circuit which sees a voltage which is the back EMF. You can do it that way. A mechanical subsystem is just the mechanical system which sees a torque. You can do it that way. First, let us do it that way, and then we will handle it as an integrated system. So, for the electrical subsystem and the mechanical subsystem, So, for electrical subsystem, what will be the kinetic energy, what will be the potential energy. So, we will put the subscript E. Okay. Half Q1 dot square LA, right. So, this is half LA Q1 dot square, that is the kinetic energy. The potential energy is Q1 is the direction in which E is added, E is applied, but it is acted on in the opposite direction by back EMF. So, the total voltage effectively applied on this circuit is E minus EB, and that acts in the direction of E Q1. So, we will have to put a minus E minus EB, sorry, EB into Q1, fine. The Rayleigh term of the electrical subsystem is half R A Q1 dot square, right. So, done. From here we can write the momentum, because momentum is what? Lagrangian is T minus V, yes. So, okay. No, only the Lagrangian. So, the P1 is the derivative of only the Lagrangian, the Rayleigh term does not appear. So, this is nothing but the momentum. You can see L is equivalent to the mass, Q1 is equivalent to the velocity. So, it is the electrical momentum. So, this is the momentum. So, now we can write your Hamiltonian function as T plus V is equal to, so what is T plus V? T we substitute it here, so that we can express in terms of P. It will be okay, it will come twice. So, 1 by twice L A in the denominator, P1 square, right, this term, minus V. So, it becomes plus E minus E B Q1. Huh? Yep, sorry. So, T plus V, it is minus, you are right. So, this is the Hamiltonian function. So, if you write the Hamiltonian function, then the rest falls in place immediately. Q1 dot is the derivative of the Hamiltonian with respect to, I will write E, with respect to P1, that is derivative of the Hamiltonian with respect to P1 is, yes, P1 by L A. Good. The other one, P1 dot is equal to, we have to use this. So, take a derivative of this and this, it is with respect to Q1, it will be this term minus of that term. So, E minus E B, because it was negative here, minus, okay, R A Q1 dot, but dot I do not want in the right hand side. So, we can substitute E minus E B minus R A P 1 by, good, equation done. Now, in the mechanical subsystem, the T kinetic energy of the mechanical side will consist of the two bodies their own kinetic energies. So, it is half I 1 q 2, yes, q 2 dot square plus half I 2 q 3 dot square, fine. Okay. Now, the potential energy would be due to the k term here, and there would be the torque applied that will be acting in the direction of q 2. So, we have to take that into account. So, it is half k, it is q 2 minus q 3, q 2 minus q 3 is the torsion in that spring, that is squared, plus F acting in the direction of q 2. So, minus F q 2. And the Rayleigh term is the two friction elements. So, half R 1 q 2 dot square plus half R 2 q 3 dot square, is that right? So, the three terms we have written down. Now, we have to express T plus V in terms of P and Q, remember that. So, we have to find out what is P or P 2 and P 3. So, P 3 P 2 is basically the derivative of this term, derivative of the Lagrangian we had written, because the derivative of the potential with respect to q dot was 0. So, we can write directly like this, q 2 dot is I 1 q 2 dot, that is P 2. Similarly, P 3 is the derivative of this thing in terms of q 3 dot is I 2 q 3 dot, obviously, because these are the two angular momenta, fine. Now, we have to express this in terms of that. So, we will have to write H of the mechanical side is, we have to express this, which means these terms we will have to write in terms of the P's that we have just derived. It will be 1 by twice I 1 P 2 square plus 1 by twice I 2 P 3 square plus the potential term plus half k q 2 minus q 3 square then minus now F q 2, k is only 1, there is only one. No, wait. We will do that later. First, let us obtain the mechanical systems stuff independently, and then we will substitute. So, this is the total Hamiltonian function. So, we can now write q 2 dot is derivative of the Hamiltonian with respect to P 2. What remains? Only this. So, P 2 by I 1. Similarly, q 3 dot will be trivial, is simple, P 3 by I 2. right, from here. So, these things are relatively easier. Let us go to the momentum terms. P2 dot, that will be, let us first write and then evaluate, H m by del Q2 minus del R. That is what? The first term when differentiated with respect to Q2 yields two terms here, fine. So, you write down them carefully, k minus k Q2 minus Q3, yeah. So, plus f okay, yes, f and this term minus R1 Q2 dot, fine, and then this has to be substituted. So, we will write minus k Q2 minus Q3 plus f minus R1 Q2 dot is P2 by I1, done, fine. Okay. The next equation would be P3 dot is what? Again just use this with 2 substituted by 3. So, you have the first equation, this remains. So, this remains only, it will be k Q2 minus Q3 and then yes, and this relative term will remain, okay, that will be minus R2 Q3 dot, which you can now substitute as R2 P3 by, done. So, at this stage your certain things remain. Where are the equations? Where are the equations finally? Here are equations, E b remained and we need to substitute that, f remained, we need to substitute that. So, just substitute them from whatever we had written earlier and put them back. The moment you put them back, you will need to substitute these because they are dotted terms. So, once you substitute, can you write down the equations now? This term will have another term, this term will have to be substituted from there, you do that, okay, I leave. So, this is how the equations for the DC motor could be obtained. You might argue that now here we took the two things separately. What if you take them as one single electromechanical system? Can't you do that? Yes, you can do that. But in doing so, when you do this kind of problems in exams, you might as well argue that I will do it as one single electromechanical system, but there has to be some cautions exercised. Let me illustrate that, because otherwise you might commit problem there. Let us do it as when we treat the whole thing as a single electromechanical system. There the variables remain the same, but there has to be some problems regarding the interaction between the electrical part and the mechanical part in terms of these. Let us see. Let us do it by the Lagrangian method first, not going by the Hamiltonian rule, because that is another method I taught, you have to learn how to use it. So, in this case the T I will write treated as a single electromechanical system then T is it will be the same, the the 3 kinetic energies half L A Q 1 dot square plus half I 1 Q 2 dot square plus half I 3 Q 3 dot square. Done. Okay. Potential energy V. Here notice what is the total potential energy? Potential energy will include the back EMF, potential energy will include the torque, and that is what we need to treat carefully. So, first the electrical part, it is minus E minus E B into Q 1, it appeared. Okay. Now, plus half K Q 2 minus Q 3 of the spring minus F Q 2, this is the torque. So, notice there was this term and there was this term that naturally appeared, they are inside the system, still they appeared. Now, we have to do something about that. So, let us first substitute what we know they are. Substitute it, you get minus E minus K phi, E B is Q 2 dot Q 1 plus half K Q 2 minus Q 3 square minus F is K phi Q 1 dot, right, K phi I A Q 2. Fine, leave it like that, and the total Rayleigh function is half R A Q 1 dot plus half R 1 Q 2 dot square plus half R 2 Q 3 dot square. Now, notice one problem. The problem is that in the whole derivation we had assumed that the V is independent of the velocities, and they are dependent now. V is now dependent on the velocities, and therefore, we cannot use exactly the same formulation, but still we can use the similar formulation because we had proceeded up to one point by without assuming that, and at some point we had introduced that assumption. At what point? When we had said that we know what the delta of the Lagrangian of the Q 1 dot is, we said that is equal to, that is what will not happen here. Where did we use it? At one stage we had obtained the Lagrangian equation as d dt of the derivative of t with respect to q 1 q I dot minus derivative of the v with respect to q I plus derivative of the Rayleigh with respect to q I dot equal to 0. This we said that if we can write this as the okay, no, here it was the Lagrangian, here it was Lagrangian. So, there was no problem here, the problem was here. We said that since V is independent of q I dot, we can substitute this as the Lagrangian. This we cannot do now. So, we will have to use this equation as the basic equation on the basis of which we obtain the equation. Everything will be the same. Go ahead, do it. In terms of this, we will have the second order equations as T first, the in the direction of the q1 will be this derivative, it will be L A q1 double dot, right, first term. Second term, the derivative of the Lagrangian T minus V with respect to Q1, it will be this term only, the other terms vanish. So, it will be minus E minus K phi Q2 dot, yes, okay, plus this term plus R A Q1 dot is equal to 0. That is the first equation. Second equation, do the same thing in where Q2 is here, Q2 is here, Q2 is here. You will have I1 Q2 double dot minus, in terms of Q2, what remains? Here it remains, here it remains. So, write it carefully, minus K phi Q1 dot plus K Q2 minus Q3 plus R1 Q2 dot equal to 0, right. The third equation will be similarly I2, I can write almost by similarity with this, Q3 double dot minus, when you do it in terms of 3, what remains? This remains, nothing else. So, I will have to write it carefully. It will be minus K Q2 minus Q3, that does the potential part plus the Rayleigh part, it will be plus R2 Q3 dot equal to 0. So, these three are the Lagrangian equations, fine, but we want to derive it in the first order, and we have already derived it, we want to see that we are doing it right. So, we define the potentials, P1 is equal to what? We have already done that. Similarly, P2 is equal to I1 Q2 dot and P3 is equal to I2 Q3 dot, right. In terms of this, fine. Now, once you have defined that, we can write the Lagrangian equation had taken the form P1 dot is equal to derivative of the Lagrangian with respect to Q1 minus derivative of the Rayleigh with respect to Q1 dot. Okay. So, P1, these we can write in the right hand side, it will be P1 dot is derivative of the Lagrangian with respect to Q1, Lagrangian with respect to Q1, this goes T minus V. So, this becomes plus and this remains, nothing else. So, it will be E minus K phi Q2 dot minus the Rayleigh term R A Q1 dot. Okay. Both the dotted terms in the right hand side. So, substitute, you get E minus K phi Q2 dot is P2 by I1 and this is here minus R A P1 by L A. So, that is the equation. Notice that equation has come out to be the same as the one that we have derived using the Hamiltonian method. Check. Similarly, P2 dot is the derivative of the Lagrangian with respect to Q2 minus derivative of the Rayleigh with respect to Q2 dot is it will be derivative Lagrangian with respect to Q2. This term will remain, this term will remain, right? Yes. So, you will have to write it as K phi Q1 dot minus K Q2 minus Q3 minus R1 Q2 dot, and then substitute these two. Right. So, you more or less understand how to do it, right? Do you? And you I would request you to check that this method is yielding the same set of differential equations that you obtained by the Hamiltonian method. So, is the point clear? Here in this case there were some forces acting inside the system, the torque and the back EMF both were inside the system. If you take the whole thing as one electromechanical system, it was not that somebody else is applying that, but then those things are also properly accounted for the moment you use the Lagrangian equation properly. Only thing is that is the character of any electromechanical device, that the torque, which is a force, is proportional to the current, which is a velocity. So, there will always be velocity dependent potentials in any electromechanical system, and therefore, we have to be careful about such things. Fine. Okay. In the last class, we had started handling some electrical circuits. There you probably noticed a problem. Let's just do one electrical problem in order to illustrate that carefully. Here we consider, say, a voltage source, an inductor, a capacitor and a resistor. Simple circuit. How will you do it? E, L, C, R, we will say simple Q1 and Q2, and we can simply write it. Fine, let us write. You will have the Lagrangian as the kinetic energy half L Q1 dot square minus the potential energy half 1 by 2 C Q1 minus Q2, then it will become plus E Q1, right, that is the Lagrangian function, and the Rayleigh function is half R Q2 dot square. Fine, no problem. So, we can directly go ahead. So, along Q1, the equation will be P1 is the derivative of the Lagrangian with respect to Q1 dot, then L Q1 dot, that is the P1. Now, if you have any difficulty, ask me. If you have any difficulty, ask me. I am the person to ask. So, you can write P1, then you can express okay, P1 is this and P2 is you have a problem there, right, it is 0. If you do it like this, Q2 dot is 0. So, P2 is 0, that is obvious, because this line does not have, this particular loop does not have inductance. P2 is 0. If P2 is 0, then the Hamiltonian is expressed as half L Hamiltonian would be the potential energy plus kinetic energy. Kinetic energy would be half L Q1 dot square. Now, this will have to be substituted. So, we will write it as it is easy to write 1 by twice L P 1 square, right, using this plus the potential function. It is 1 by twice C q 1 minus q 2 square minus E q 1, done. That is the Hamiltonian function. Okay. Then we can write the equations directly. Q 1 dot is the derivative of the Hamiltonian with respect to P 1 is simple. Here P 1 by L. Where I have written the Lagrangian, I have not put you are right. So yes, whenever I make such careless mistakes, please point out, because that goes into the recording. Okay, fine. So you have Q 1 dot is this, and then P 1 dot is minus delta R delta Q 1 dot is, you can easily write now, yes, minus 1 by C Q 1 minus Q 2 and plus E, right, done. Right hand side does not have any dotted term, so we are happy. Then along the Q 2 direction, we have Q 2 dot is P 2 dot is what? Yes, same thing. So 1 by C Q 1 minus Q 2, only the sign is different, minus, in this direction there is the Rayleigh term. So it will be R Q 2 dot. So what are the ultimate final equations? It is 1, 2, 3, right, these three are the equations. Wait, I have not yet talked about the Q 2 dot thing. I have written it, but wait. Q 2 dot is the derivative of the Hamiltonian with respect to P 2, which has turned out to be 0, which has or in other words, it cannot be evaluated, it could not be evaluated, but still where is P 2? Is 0. P 2 is 0. If P 2 is 0, P 2 is always 0. What is P 2 dot? Obviously 0. So if P 2 dot is 0, actually this is not correct. This is all that we can say is we could not evaluate it. If P 2 dot is 0, we now have Q 2 dot, right. From here we will be able to write Q 2 dot is this goes in the other side, 1 by R C, can you see? Yes, Q 1 minus Q 2, that is it. Okay. When you write this, it was actually wrong, you could not evaluate it from what you have. So we have taken a different route, and that argument was sound, since you know that your P 2 is 0, P 2 dot also has to be 0, there is no change in that, and so this term is 0, and therefore from there you can extract. So that gives you the equation 3. Good. Which this equation? we had obtained this. Now, in the left hand side it is P 2 dot, which we have argued that it is 0. So, if you put 0 here, then you can extract this. Fine. See, you needed 3 equations, but in the circuit there are only 2 storage elements, and the minimum number of equations that you really need is equal to the number of the storage elements. So, we had done all this exercise, but ultimately ended up with 3 equations, which is not very economical. They are all right, they are all correct, but they are not economical. So, the conclusion is that this Lagrangian Hamiltonian formalism that we are taking, this often leads to uneconomical set of differential equations, but they are all right, they are not wrong. And we will have to learn how to obtain the correct economical set of differential equations. You might argue that this problem happened because we sort of blindly took the q1 and q2 as the coordinates, the 2 loops, and these 2 loops independently may not be the minimum or correct set. Fine, let's follow that line of argument. Let's see where we end up. It is the capacitor here and the resistor here. Instead of defining the loops, this time what we will say, we will argue that the current or the charge through the inductor is one state variable q1 and the charge through the capacitor is another state variable q2. You can do that. So, we are not using the mesh current kind of argument, we are using a different argument to see whether that helps. Here is your E, here is your L, C, R. Then can you write the Lagrangian and the Rayleigh? The Lagrangian will be, in this case, half L q1 dot square due to this, now minus due to this it is 1 by twice C q2 square. Now, it will not be q1 minus q2, q2 square plus E q1, right, and the Rayleigh equation would be simply, now this term, how much current flows through this? q1 minus q2. So, here it will be half R q1 dot minus q2 dot square. Fine. Now, therefore, P1 is the derivative of the Lagrangian with respect to q1, it will be L q1 dot, fine, no problem. P2 will be derivative of the Lagrangian with respect to q2 is 0. So, in this case also we get it 0, there is no problem about it, it is still 0. Oh, sorry, q2 dot is 0, q2 dot does not appear in this equation. Fine. So, if P2 is 0 and P1 is this, then we can write the Hamiltonian as 1 by twice L P1 square and the rest remains, it will be plus 1 by twice C q2 square minus E q1. Okay. So, now your you can either write q1 dot is equal to simply P1 by L from here, or you can write q1 dot is the derivative Hamiltonian with respect to P1, which is same thing. So, it is not really necessary to evaluate these automatically follow from the definitions of the P1, P2. Q1 is this, and I will not bother about the Q2 at this stage, because here there is something wrong. Let us do it for P1 dot is minus derivative of the Hamiltonian with respect to Q1 minus derivative of the Rayleigh with respect to Q1 dot is what? When you write the Hamiltonian with respect to Q1, only this survives, only this survives, yes. You will write E minus, yes, the Rayleigh term survives, R times Q1 dot minus Q2 dot, fine, and P2 dot is same thing with respect to Q2, it will be minus 1 by C Q 1 by C Q2 plus R, again this term will remain Q1 dot minus Q2 dot. Okay. Now, you would notice that P2 is 0, fine, P2 is 0. This implies P2 dot is 0. Okay. If P2 is 0, P2 dot is 0. So, you have Q2 dot is what? Q2 dot is, there will be something in the right hand side. Wait, we could not extract it from here. Q2 dot is the derivative of the Hamiltonian with respect to P2. So, how do you write it? Yes, this will not give. Here you have, this will be 0, we know this, and therefore, this is obtained. So, we will not use this, we will use this 0 is equal to minus Q2 by C plus R. Q1 dot we already know is P1 by L, P1 by L minus R Q2 dot, fine. So, you have Q2 dot is, you can now extract it, minus Q2 by R C plus P1 by L. So, this is how. Ultimately, what are the equations you have? Ultimately, what are the differential equations you have? Tell me. This is definitely one. This is another. Yes. So, you still ended up with 3 equations. So, this actually did not help, and we need to still refine this, and in fact, the proper methods, okay, you know that for electrical circuits which are pure electrical circuits, we have the Kirchhoff's laws for defining how the currents and voltages are distributed and their relationship. We will show then that can be used in order to formulate the minimum set of equations, but that will also tell us how to formulate the correct variables for this formulation. So, that is what we will take up from the next class. Typically, for electrical circuits, how do we obtain the minimum set of differential equations? Fine. Okay, that is all. Thank you.